The most common form of the Bayes theorem used in statistics is the parameters on data form, not the events form. So instead of having probability of A given B, we now use probability of theta given D. And theta is a Greek letter that is a generic letter that we use for a parameter. And we can have here different parameter values. And D stands for data. So we can have different data values. So here as an example, as shown in the right side of the screen, the theta can take values from 20 to 80 and is a continuous variable. So it can be an infinite number of values between 20 and 80. And data the same, but between 0 and 100. So the theorem says that in order to obtain the posterior distribution, which, as I mentioned with the events form, here is an infinite number of values between 20 and 80. So we need to determine the probability for every of these values. And data can take also many values. So now, in the case of discrete cases like before, we can have a discrete number of cases, but here we've got an infinite space of possibilities. So the analysis becomes much more difficult. But the logic is exactly the same. So let's go ahead with the theorem. So probability of theta given data, so is the posterior distribution of the possible parameter values after I've observed the data. And that's calculated with probability of data given theta, which is if given a parameter value, what's the probability of observing any possible value. And that is multiplied by the prior probability, which is the probability we give to each possible parameter value before we observe the data. And the components of the numerator are multiplied, and then they are divided by the probability of the data. Probability of the data is very, very difficult to calculate. That we sometimes don't even calculate it, and we settle to just determine that the posterior is proportional to the numerator in this equation. Now, as I mentioned, for the events case, we typically have information about the prior and the likelihood. In fact, we provide that information because we provide the prior. And in this case, we say that theta is normally distributed with a mean of 50 and a standard deviation of 5. And for the probability of the data given theta is normally distributed with a mean of theta and standard deviation of 5. We'll see that later. So now we are going to go to the grid below, in which I'm going to present the prior and the likelihood, and then the prior times the likelihood. But instead of using numbers that I use in the events case, we have infinite number of possible values, so I cannot put infinite number of probabilities as I did in that case. So I'm going to use colors that indicate where there is more probability than in other places. We've got the prior distribution on the right hand side, then the likelihood or the probability of the data given the parameter values, then the prior times the likelihood, and on the top left the posterior distribution. On the bottom we've got the probability of the data. The goal then is to use this tool to be able to understand how the posterior appears, or how the posterior is calculated. So, and remember that we are going to use color in order to represent which probabilities are higher than others. So on the bottom right of the screen, you have a key of the probabilities. So pink would be the higher probability, then red, then orange, then yellow, then green, then blue, then violet. And you can see that in the prior distribution, that's we chose that distribution, and so that's why the color is there. You can see that in the axis goes from 20 to 80, and in the middle, which is 50, that's the higher probability. And when you go away from the middle, you have lower probabilities. So probability of the data given the theta, that's independent of the prior. So it has nothing to do with the prior. If the theta is a value of 80, then what values are expected in the data? Well, the values that are close to 80 are more likely, and values that are away from 80 are less likely. And that for every possible value of of theta. And that then the way we obtain the prior times the likelihood is by multiplying the values of the prior, which are represented by the color, and times the values of the likelihood that are also represented by the color, and that gives us the prior times likelihood. So you can see there that is more concentrated towards to 50, and values at the extremes are less and less and less likely. And that, well, the way we calculate that is sometimes you can do it numerically if it is easy. Sometimes we've got some probability distributions of the prior distribution and the likelihood distribution that work very well, and we are able to determine the prior times likelihood very easily. Sometimes is done by a simulation. It's not a numerical solution. So when you've got that, then you've got to add all the vertical values. If you think about dividing the sample space into tiny columns, and then you add all those values that are represented by color here on those columns, and that would be the probability of the data for that possible value of the data. And you do that for each of the columns, and that you get a distribution of possible data values. Of course, this is not the way it's done, because we cannot do it mathematically. There are infinite number of values, so you don't do that. There are many ways of calculating the probability of the data. It's complex, and sometimes it's even not calculated. So until now we've been working before collecting the data, so everything we've done can be done before collecting the data, and we can actually make predictions of the data, what data is expected under the model we created. Now let's consider that now we collect the data and we observe the value of 40. So data is now 40. So that means that we are going to work with only the column that contains the value 40 of the data. So in the second grid from the right, the likelihood, if we consider just that column and consider there is a very tiny column that only contains the value 40, so those values that are there correspond to the likelihood. And remember, those values are not going to add to 1, they are not even to integrate to 1, because likelihoods don't do that. Now, but we multiply now all the values of the prior for all the possible parameter values times all the values of the likelihood, and that gives us the probability of the data given the parameters times the probability of the parameters, which is the prior. And if we add all those values, now we've got the probability of the data, which is indicated in the bottom grid. So now we've got the numerator and the denominator of the Bayes theorem, so we can now divide each value of the numerator by the probability of data, which is only one value, and then that gives us the posterior distribution. We indicate that the values that we are calculating are proportional. It's not an inequality. So, but that's the logic. Even if we don't do this exactly, that's the logic of the Bayesian parameter and data version of the theorem. We start with a prior distribution that we create. We also choose a function, which is in both cases was a normal distribution for the likelihood, and then we combine these two in order to obtain the values of the numerator, and then by using only the values on that correspond to the data we observe, we calculate the probability of the data, and then with these two values, then we come up with the posterior distribution. So if you see how the posterior looks like, in the prior the values were around 50, but now that we observe the data 40, the posterior distribution is the values, the higher probabilities are between 40 and 50, somewhere in the middle, because the posterior distribution takes into account the data we observed, but also the prior distribution. So it's a combination of both. So now I will show you a typical way of representing. So if you see textbooks and papers, you won't see the grids I generated. So the most typical way is to representing on the x-axis the possible values, possible parameter values, so theta, possible values from 20 to 80 in this case, and it's a normal distribution with mean of 50 and a standard deviation of 5. So more or less that's the way I'm representing it there. And then the likelihood would be with the way that I represent it, but it looks like a distribution. The difference that this distribution doesn't integrate to 1. So it's not a probability distribution, is going to be called the likelihood for that reason. So now we are going to generate the likelihood. And the likelihood will center around the value of 40. Why is that? Well, because we observe the data being 40, and in the probability of the data given parameters grid, the second from the right, if you see the column that corresponds to 40, then the parameter value 40 is the most likely. And then probability of the data is represented by the yellow color in the bottom grid, but we don't know the exact value in this case. We are doing this by illustration. And the posterior, the mean will be somewhere between 50 and 40. So because it's a combination of the prior and the likelihood.